But just to give you an idea for now, these are the task manager screenshots from our 8-core machine for the two alternative solutions, and you can see that the utilisation in the Blueprint implementation is far superior to that of the TPL Parallel 4 implementation. So let's take a look at the serial first approach in a bit more detail. The first problem we find is that the optimal solution is just far too complex to implement bottom-up. And that means that we artificially introduce synchronization points. The graph on the right shows the latent concurrency of this application with time. And what we can see is that it generates a large number of jobs at the start and then counts those down to synchronization points, so we can see it stepping down there. We've drawn horizontal lines on these diagrams to show the number of CPUs. So all of the jobs that are above that line are ready to execute but can't be because there isn't a processor to run them. They're all busy. And when the number of jobs that are currently being executed by processors falls below that line, we've shown that in pink. The pink space there is the idle CPU. So if we look at the most extreme case here at the bottom where we've got 16 cores, we create a large number of jobs at the start, but the stages that follow don't generate enough jobs to keep the CPUs busy. And so we have a lot of idle time until we get around to the next iteration. Now, if the number of jobs don't divide evenly into the number of CPUs, then this effect becomes worse. Because it might be that at the end of the first stage, there's one job left over. The second stage can't start until that's finished. But that one job is going to take the same time as the previous 16, because 15 of our CPUs will remain idle. And this problem can become worse if the job durations are variable as well, so with non-deterministic calculations. Parallel first works differently. Blueprint applications have a completely parallel top-level code, and Blueprint makes it very easy to introduce pipelining. And you can see the effect of this in the latent concurrency profile on the right, which is the equivalent for the Blueprint implementation. So instead of having huge peaks and then the concurrency dropping down below the number of CPUs, it's kind of smoothed it. And that's because it's already started the next iteration while it's still working on the previous one. Now in theory there's nothing to stop you doing pipelining like this with a serial first approach, but the complexity does become prohibitive for anything but the simplest applications. So Blueprint makes it very easy, and this means it's easy to ensure that the latent concurrency is kept high all the time. So there's plenty of jobs available for processors to pick up. And because the iterations are sort of smoothed into each other like this, we don't get that problem that we saw in the serial first implementation, where there's just one job left over from the first stage that's going to hold up all of the following stages, because all of the stages are running in parallel here. And so whereas with the serial version we had to minimise the size of that job to reduce the impact, we don't need to do that for parallel first. We get excellent load balancing even with large jobs. And this means there's no need to introduce parallelism down at the low level. Let's just take a quick look at the runtime overhead involved with the two approaches. In the serial first case, runtime overhead is critical because there's so many jobs. So we're frequently signalling workers and we're frequently manipulating job queues and that sort of thing. So therefore it's kept to an absolute minimum. In the parallel first case, the per job overhead is larger than the serial first, but it's still negligible in comparison to job duration. And actually it's not significantly larger than serial first. And what you get for that is more complexity and functionality, and that leads to gains in load balance that just make the overhead insignificant. And in actual fact, because we typically schedule less jobs with the parallel first approach, the total overhead could in fact be less than the serial first approach, and you can see that represented in this graph on the right here. The serial first has a small per job overhead, the parallel first is slightly larger, but because the serial first is scheduling so many more jobs, the total overhead, which is the area of these rectangles, is actually larger for SFPL, but that depends on the application. There's a couple of important considerations for achieving optimal solutions. Large indivisible tasks give Amdahl effects, and to mitigate that we need to overlap iterations, as we've described previously, in order to keep the CPUs busy. In addition to that, we need to prioritise, and the reason that we need to prioritise is because in a processing chain, it's important to run the biggest blockers first. And that means that if you've got a job that's blocking, say, 20 parallel tasks, and you've got a job that's only blocking one task, you want to run the job that's blocking the 20 first, because that's going to put your latent concurrency up nice and high, give you plenty of jobs for the CPUs to pick off, and keep the system busy. Now, if these issues aren't properly addressed, then they can completely kill the utilisation and load balance, and it gets much worse as the core count increases.